Okay, another video to watch to learn more about solar, and this time is the electricity is really flow. Let's see.
This episode was made possible by generous supporters on Patreon. Hey crazies, welcome to part 3 of our series on electrodynamics! In part 2, I made the following comment. We usually have a bunch of charges moving together in something we call a current. I think that deserves a little more attention. If you've been watching this channel for a while, you know that language is tricky business, especially in science. You have to be careful with your word choices. The word current is usually used to describe a fluid like water moving continuously in a certain direction. But does charge actually move like water? We certainly thought it did when we gave it that name. But to answer this question, we need to delve a little deeper than usual into materials. First, materials are made of atoms, a bunch of protons and neutrons surrounded by a cloud of electrons. Those electrons are the lighter, looser particles, so they do the moving in materials. Second, we like to divide materials into 2 categories, conductors and insulators. A conductor is a material that freely allows the flow of charge. An insulator is a material that does not allow the flow of charge. Either type of material can become charged. What matters is whether or not the charge can move once it's there. Category alert, category alert, category alert. Okay, I'll mention it. Stop! Quick disclaimer, always be cautious of categories. They give us these little bite-sized pieces our limited brains are capable of understanding. But reality consistently resists that kind of simplicity. Like most things, materials fall on a spectrum. Conductors on one end and insulators on the other. No material is a perfect example of either type, but the 3 best conductors are silver, copper, and gold, in that order. It's no coincidence that those all fall in the same chemical group. They each have one very loose electron on their outer edges. That alone doesn't make them a good conductor though. A material isn't made of one atom, it's made of a bunch of them. We need to see how those atoms work together. Atoms are always bonded by their electrons. In metals like copper, the electrons tend to form one big cloud for the entire material. So this really comes down to the quantum states of the electrons in the material. Specifically, the energy levels. In a single atom, electrons can be in a variety of energy levels. But when atoms are together in materials, those levels are separated into bands, a conduction band and a valence band. The lower energy levels don't matter because they're buried. What separates conductors from insulators is how much energy it takes for an electron to jump from the valence band to the conduction band. For insulators like glass, the gap is really big. In semiconductors like silicon, the gap is small. In conductors like copper, there is no gap. Valence electrons are conduction electrons. That's what makes them so conductive. There are already electrons in the conduction band, ready to go. If they get a reason to move through the material, they'll do it. But is that how water moves? Well, kind of. We want to be careful with our comparison here. The analog for charge is the water. Those are normal scale things. The analog for a single electron is a water molecule. They're microscopic things. We need to keep those 2 things separate. Let's consider water first. Say you've got a long pipe with some water at rest inside. The water molecules look like this, moving around randomly. If the water begins to move through the pipe, the molecules move too, because they're what make up the water. They still have the random motion, but they now also have forward motion. A similar thing happens with the charge in a copper wire. That wire is full of conducting electrons, just like the pipe was full of water. Individual electrons are conducting around the copper randomly. If we connect a power source though, it'll act like a pump. The electrons will still have the random motion, but also some forward motion. Except electrons are quantum particles, so we don't know where they are exactly. You never let me get away with anything. Nope. Okay, so according to quantum mechanics, if we know the energy of the electrons, we don't really know their position. Those measurements are mutually exclusive. We don't really know where individual electrons are in this wire, but we do know the whole collection of them is drifting forward. In fact, there's something called drift velocity, which tells us how fast that drift is. And it's a lot slower than you might think. In this copper wire, it's only about 1.5 inches per hour. That's 4 centimeters per hour. Wait a minute, then how come this flashlight turns on instantly? Because changes in the electric field transfer at the speed of light. A flashlight is pretty simple. A couple of batteries, a light bulb, and a switch. It could easily take an hour for the charge to get from the battery to the light bulb. But once the switch is flipped, the battery's electric field travels across the circuit at the speed of light. And all the charge in all the conductors moves at nearly the same time. How cool is that? Anyway, charge moves a lot slower in a wire than water does through a pipe, but that's okay. Electric current isn't about speed. It's measured as the amount of charge over time, not distance over time. There's a lot of charge in a wire, so a high current doesn't actually need to move that fast. But does the charge move through the entire volume of the wire? Sure. Well, at least when the current is direct. All right, one more thing. There are 2 different ways charge can flow. Direct current, or DC, which is a steady flow in one direction, and alternating current, or AC, which is a continuously changing flow that goes back and forth. Can't you do either of those with water too? Well, yeah, but there's something hiding in the details. The inside edge of the pipe can put drag on the water, so it moves more freely near the center. For electric current in a wire, it's the other way around. The behavior of the atoms in the center restricts the number of electrons that can flow, so they actually move more freely near the edge. In DC, electrons flow through the entire volume in spite of this. But for AC, the flow is mostly limited to the outer edges. It's called the skin effect. What was the original question again? Does charge flow like water? Right, yeah, kind of. If you're not concerned with where the moving charged particles actually are in the material, then water flow is a good analogy for electric current. So good, in fact, it has a name, the hydraulic analogy. There's a hydraulic equivalent for every circuit component you could imagine. It's kind of fascinating. So, got any more questions about electric current? Please ask in the comments. Thanks for liking and sharing this video. A special thanks goes out to Patreon patrons like Kenny Holmes, who help keep the show going with their generous support. Don't forget if you'd like to keep up with us. And until next time, remember, it's okay to be a little crazy. By far, the most